This is a help video for the Laplace Analysis Game, Level 3, Problem Type 1. So we're going to assume that you've already viewed the introductory tutorial associated with the Laplace impedance simplification game, which contains a lot of very important information on how to work these problems in the Laplace domain. Also, we do strongly recommend that you look at examples prior to starting an exercise, which are available here. That will help avoid a lot of frustration later on. So let's go ahead now, and I'm just going to jump into a problem at level 3 here. And this is going to be a superposition type of problem, which is a little bit lengthier than the lower level problems, because we will have to analyze several, actually 2 child circuits here. So here's our problem, and we're instructed to analyze it using superposition. So the first step, however, is always to take this circuit and transform it into the Laplace domain. So here we have the henries, the farads, and the time. We have 2 independent current sources. They're both step function sources. So now we're going to transform that so the resistors stay the same. The sought current has been rewritten as I naught bar, or bold I naught, which indicates it's in the phasor domain now. It's a function of S rather than T. And for the 2 Henry inductor, we remember the inductive impedance is given by SL, so that will just be 2S ohms. For the current source, we can remember that I1S of t is just this 4U of t, so hopefully remembering that the Laplace transform of that is just 4 over S. And if you ever need Laplace transform pairs, they are available from this table. Then the 2 farad capacitor becomes 1 over SC in impedance, so that's 1 over 2S. And we have to put the 2S, as always, in parentheses there to make sure it's all in the denominator. And finally, for the I2S of t source, that's 9U of t, so that will just become 9 over S in the Laplace domain, using the standard well-known Laplace transform of the unit step function. Okay, so now we can check all of that. That is correct. And now it'll go ahead and redraw that circuit for us in the Laplace domain. And remind us that we do need to use superposition to get credit for the problem. So that means we need to begin always by killing sources. That is, by deactivating one of the 2 current sources at a time. So we'll click on that to go into the circuit editor in that special mode for killing sources. And so we can kill either one. Let's just maybe do this one first, I guess. And it does give us some instructions there. And actually, put that back, belongs up here. Okay, so I'll just delete this source. Now remember, because these are our current sources, we need to change them to be 0 current. So 0 current means an open circuit, not a short circuit. A short circuit can have lots of current. So this needs to be deleted. We can either use the delete key here or just use the delete key on the keyboard. Either way, we've killed that one source. We'll keep the other one now. We never want to kill all of them, of course. And then we'll just click Done Killing Sources. That's all we can do in this mode in the circuit editor. Okay, so we'll wait for that to come back out. Okay, it takes a moment here because it's doing a lot of calculations behind the scene. Okay, so now, and by the way, you might notice one of these buttons is now blank. That's a sort of a glitch in this software framework we use. So the button will still work and you can still see its tooltip, but occasionally, on rare occasions, that will happen. So just use the button normally and it won't be a problem. Okay, so now I'm going to go ahead and simplify this circuit to make it into a simple current divider. So I'm going to go back into the circuit editor in that mode. And by the way, to recover from that blank button, you basically have to go out of the program and back in. But it will still work fine if you're in the middle of a problem, just to continue. Okay, so I'll wait for the circuit editor to come up here. Okay, and it's once again giving us some instructions for that. And it reminds us that right-clicking is very important when you're using the circuit editor. Okay, so now I want to combine elements in series. For example, these two elements are part of the same two meshes, the outer mesh and then this mesh. So they're clearly in series, connected by a single node. So we can just change either one of those. I'm going to make that 2s plus 3. And then we also need to change the type of element there because it's no longer purely inductive or purely resistive. So it has to be changed to a generic impedance, which would be the rectangular box there. If you don't do that, it won't let you proceed. And then this one, since we're basically putting that value into here, we need to make this zero impedance, which means it needs to be a short circuit. Not an open circuit by any means, because that would mean that none of this was ever there. And indeed, it was. Okay, so we'll check that combination. Remember, we have to check one combination at a time in the circuit editor, just so that it knows what you're doing. And then we have to wait a moment here for that to register. And again, because it's doing algebra behind the scenes, it does take a little time here. Okay, and now we're going to combine these two in series also. Once again, these are in the same pair of meshes, this mesh and this mesh. And we are allowed to do that even though, oh, and it's the correct button there. We are allowed to do that even though one of them has a SOT current, because that same current goes through both of these elements, and therefore there's no problem in combining those. Now, if we had a SOT voltage, for example, then we would not be able to combine this without first doing what we call a SOT variable transformation, changing that SOT voltage into a SOT current, which is allowed in this mode of the circuit editor, but we don't need to do that in this particular problem. But sometimes you might, so keep that in mind. Now let's combine these two values. So 4 plus 1 over 2s, well, we can kind of imagine that that's going to be, we put it over a common denominator, so we basically multiply this by 2s over 2s, and so that's going to give us 8s plus 1, the quantity 8s plus 1, divided by the 2s common denominator. And then once again, that's still red because we need to change it to a generic impedance, which the note there was explaining. And that should be correct. We can check that that gives us the 4 ohms, which we had here, and then 1 over 2s. So that indeed works out to that. And then we have to also change this again to a short to complete the combination. And now we'll check that. And that is correct. And once again, we have to wait for that to tell us it's correct. There we go. Okay, and if you wanted to close up that circuit a little bit, we could just use the compress tool to make that a little bit neater. It doesn't really matter for the purpose of the problem. But in any case, now I'm going to complete the editing because we now have a current divider, and that's sufficient. We don't really need to do any further simplification. We could, but it's not really necessary. And we'd have to do a SOT variable transformation in doing that. So I'm going to exit the circuit editor now. And remember that we're working with one of the child circuits here. This is not the entire problem. So everything is primed that for the SOT variable. That means it's only a portion of the total SOT variable I naught. Okay, so now because this is a current divider, we can do single node pair analysis. So I'll select that mode to write the equations. And we just basically want an equation directly for that SOT current, that SOT branch current, since it goes through one element. And so it'll give us the appropriate palette there. So I naught prime is equal to, and now we have a choice of several different terms we can use. That's really just a matter of taste, how you want to do it. I think I'm going to pick this one here, which has the impedances. And so first we need to put in the value of the current source, which is I1s, so that's just going to be the 9 over s. Remember, everything here is an algebraic expression rather than just a number. And also we want to check, very importantly, polarity always. Polarity, polarity, polarity. So we observe that this current goes up here. It's then going to split. Some of it's going to go this way and some of it's going to go this way. And this current will be consistent with the direction of I naught prime. That means we do have a plus sign here. But of course, if that were pointing the other way, then we would need a minus sign. So very important to always check that. Otherwise, you can get a lot of wrong answers. Okay, now we'll remember that for a current divider, because the natural thing is really to use admittances rather than impedances. When you use impedances, the other impedance goes in the numerator. And so that's going to be the Z2 value goes in the numerator. So that is 2s plus 3. And I don't need parentheses because that's in its own text box. And then we need to put that in the denominator as well. And then we add the other impedance to it, which is going to be the 8s plus 1 over 2s. So 8s plus 1, and remember we do need parentheses in the numerator there, or square brackets, either one is fine, to enclose the entire numerator. Otherwise we wouldn't be dividing by the entire thing. So then we put the denominator again, that also requires parentheses to make sure that we're dividing both by the 2 and by the s. Okay, so that should be hopefully correct there. So we'll check that equation. And that is good. Now we've written all the equations we need for this particular child circuit. So we're going to hit this button here, which, while we can't read it, it's basically says that we're done writing equations. And now it's going to ask us to basically simplify this expression. And notice you may have seen in other problems where it says, oh, we have to factor any quadratic terms. It didn't tell us that here, and that's because we're not going to take the inverse transform of I naught prime. We're going to wait till we get the full value of I naught from both of the current sources before we do that. So we don't need to do that here. Okay, so now let me pull up my algebra here that I've done. And so to work this out, I've copied this over. I naught prime is 9 over s. And we know that's amps, which it should be. So I drop the amp, and the ohm will cancel with all the ohms here. So we've checked the unit consistency, which is always good to do, because if its units are inconsistent, the answer can't possibly be right. So we have a 2s plus 3 here divided by a 2s plus 3. And then we have that sort of composite fraction there, the 8s plus 1 over 2s. Now we never want to have fractions containing fractions, so we need to rationalize that. And the way we do that is we're going to multiply both the top and the bottom of this fraction. We'll keep the 9 over s out front, but multiply the top and the bottom by the 2s, which is the common denominator of the denominator, basically. So that puts a 2s factor in the top times the 2s plus 3. Still have the 9 out front. And then here, when we multiply by 2s, the first term will give us 4s squared. The 2s times 3 will give us 6s. And then we have, now the 2s is gone here, so we just have 8s plus 1 remaining. And we need to make sure we remember all those terms. Okay, now, again, I always recommend simplifying things as soon as you can. It makes life a lot easier. So here we have an s and an s. Those cancel out. Don't carry through extra factors that don't belong, because you just won't be able to do partial fractions if you do that. So you need to make sure you always cancel any poles and zeros that do cancel each other. Okay, so now the top just becomes 9 times 2 is 18 times the 2s plus 3, and then we just combine this. So we have the 4s squared plus 14s plus 1, which I've written here. So now we're done with that form, and we can just enter it into Circuit Tutor. So type 18 multiplied by the 2s plus 3, which have to be, of course, be in parentheses as always. And then we divide that by, now I'll put a parentheses here. We have a 4s squared, using the caret for the square, plus 14s plus 1, close parenthesis. We don't need square brackets there because there's only one term in the denominator. So that should be correct, just proofreading it. So we'll check that. And indeed, that was correct. So that's now printed for us. And now, when it finishes registering that, it's going to tell us, okay, we finished analyzing a circuit with one source active. Now we need to analyze the other source. And so we're going to go back into the source killing mode in the circuit editor. wait for that to load up. So we've already determined the value. Well, okay, it's going to take a moment here. Okay, so we've already analyzed the 9 over s source. So now we don't need that one anymore. That's the one we're going to kill for this circuit, leaving the 4 over s source. So again, I just hit the delete key. We don't change that to a short because that's not zero current. We need to have zero current here. That means an open circuit. So we'll delete it as the same as an open circuit. Okay, so we're done there. That's all we can do in this mode. So we'll click done killing sources. And by the way, if you do have labels that are getting on top of each other, which can happen sometimes in Laplace analysis, you can select that element and click these buttons to move that label up or down so that things don't cover each other up. So that's just a way of dealing with sometimes lengthy expressions that can occur in the circuit editor there. Okay, so we'll wait for that to settle down and get happy. And finish coming out of the circuit editor. Okay, so now we need to probably simplify that so that we can once again have a current divider. So we'll go back into the circuit editor in the different mode here so they can check things for combinations. It has trouble doing all of those things in one mode, so it's much better to do it this way. Okay, so here we just have 2 resistors simply in series. They both have the same current, so it's perfectly fine to combine those. And so I'm just going to change the 4 here to a 7. And then this one, and notice, of course, these were in the same pair of meshes, the outer mesh and the left mesh there, so they are definitely in series. And then I need to, since I'm getting rid of that resistance, I need to change it to 0 resistance, which is a short, not an open. Of course, an open would leave this dangling, which is not what it's supposed to be. Okay, so we'll check that combination, and that is correct. And we just have to wait a moment here while it does some bookkeeping. Okay, and now we have the 2s ohm and the 1 over quantity 2s ohm. Those are also in series. They belong to the outer mesh and the right mesh. So now we can combine those as well. And so if we just think about it, 2s plus 1 over 2s, we'll need to put those over a common denominator of 2s, which means this one has to be multiplied by 2s over 2s, which means it becomes 4s squared all over the 2s. So I'm going to change the one on the bottom here to be the quantity, put parentheses here, 4s squared plus the 1, okay, all over the 2s. And again, because that's now a generic impedance, we do have to change the element type. We didn't have to do that here because it's still a resistance. And then this one changes to a short circuit again to absorb all the impedance so that this has 0 impedance here. And then we once again check our combination, and that is correct. And we'll wait for that to register. And like I said, if you get these long labels, if they start interfering with something else, you can just click on the element. I'll just demonstrate that actually so you see how to do it. We just click on that. We can move that label down to wherever it's convenient or move it up. Just don't move it too far so you forget what it's associated with. Okay. Anyway, we're done editing now, and we'll just exit the circuit editor. Since it's now a current divider, that's fairly easy to analyze. Okay, so we've come out of the editor now, and once again, because this is a single node pair circuit, we can use that type of analysis. It's not a single loop, as you can see, because it has 3 loops. And once again, we're going to write directly an equation for the SOT branch current. That's actually the only option it's going to let you do here, because that's just a simple current divider formula. So we have I naught double prime now as our SOT variable, if you can read that. And well, maybe for just sake of argument, I'll use a different term type this time just to illustrate. We could use the same type, but maybe I'll just do it a different way. So now we need to put in the current value of the source, which is the 4 over S in this case. And we also, once again, always need to check polarity. Very, very important. So we think about this current, it's going up, and then it's going to go this way, and some of it's going to go that way as it splits or divides. Well, we see that part is going to be going opposite to I naught double prime. That means, in this case, we absolutely have to have a negative sign there. You can't put the negative sign up here or down here because these are supposed to be the actual admittances, and those are not negative, so it needs to go out front. Okay, now remember that these are admittances represented by the letter Y, as opposed to impedances represented by the letter Z, like we use here. And remember that Y is 1 over Z, as always, and the units here are the Siemens, not ohms. That's how we know that that's an admittance, is from the units. Okay, so when we're using an admittance formula with a current divider, it's the one of interest that goes in the numerator. So this would be not 7 now, but we need to use the proper admittance, which is the reciprocal of this value. So that's going to be 1/7, and I can actually just type it as a fraction if I like. It'll convert it automatically. And then here I can put 1/7 as well. And then we have the other one is going to be, this is the Z1 value, so the Y1 value that corresponds to that is the reciprocal again. So that's going to be the 2s over this denominator. So I'll type that as 2s divided by parentheses 4s squared plus 1. And again, I didn't have to use admittances if you're not comfortable using them. It's not obligatory here, but it's just another way to work the problem. Okay, so having done that, just double check that. It looks like everything's okay, so we'll check that. And indeed, that is correct, and it's already evaluated those fractions for us, so we didn't have to do that on a calculator. Of course, you may know that that's the value of 1/7, but anyway, now we're all done, so we're going to use our next step button here. And now it wants us to simplify that. And once again, we're not going to have to factor anything here, even though it will be a quadratic denominator once we clear the fractions, because we're going to still add it to this value. So there's no real reason to be doing partial fractions on this. So we're going to take this value, and I've copied that over here now. So we have the negative 4 over S. We know it's amps. That's consistent here. And then the Siemens are going to cancel out, so that's all fine. And then we basically, well, I actually did this over here in terms of impedance, so you'll forgive me that these don't match exactly, but it's algebraically equivalent anyway. So when I did an impedance, I had the other impedance, which was the 4s squared plus 1 over 2s, and then I had the sum of the impedances, which was this plus this. So that's just actually an illustration of a different version of this formula. So here, now I need to, once again, clear fractions. You never want to have fractions of fractions. So we'll multiply here by the common denominator of both the numerator and the denominator, which is 2s, since they both have the same fraction there. So we multiply the top and the bottom by 2s. So we have negative 4 over s still, times now just 4s squared plus 1 here. And here this part remains 4s squared plus 1. But then we're also going to have, which is the 4s squared here, and there's the 1. But then we multiply by the 2s, this becomes 14s. So I put that in the middle to have the standard order of the polynomial, the way we normally do it. Okay, so that's our answer, and we'll just type that in here to let Circuit Tutor check that for us, as it likes to do. So we're going to have negative, oops, that was not negative, there we go, negative 4 over s, and that's consistent with order of operations to multiply that, so I'm going to then put 4s squared plus 1, but if in doubt you could put parentheses on the other term as well, but it's not really necessary because the 4s squared plus 1 is going to be in the numerator here because it's not enclosed in a bracket. And so then we divide that by a parentheses here, which is 4s squared plus 14s plus 1. Close that parenthesis. And oh, but actually I can't do that. So let me think here. let's see. Oh, you know what I need to do is, I'm actually not allowed to write it this way. So in this case, I'm going to take that s and put it in the denominator, which is really kind of where it belongs anyway. So I'm going to put a square bracket here and put an s in the denominator and then close the other side by a square bracket. So actually, yes, I have to do it that way because it doesn't allow us to have more than one division sign unless we're doing a simple numerical fraction, which of course this is not. Okay, so that's the form in which it likes to enter it. And again, if you have any questions about the rational function syntax requirements, you can always click this button to remember what the requirement is. And it was actually telling us what was wrong too, that we had more than one division sign, which it doesn't like. Okay, so that's the form there, and that should be correct, so we'll check that. So now we have our I double prime, and that's being printed for us here. So now we have both of those, and now we need to apply the superposition principle, which means basically, as you know, that we need to add together those two values. Okay, now it's going to notify us here that at this stage we are now getting ready to do inverse Laplace transform, and so we'll need to do partial fractions, and therefore it wants us now to factor any terms in both the numerator and the denominator. Now the reason we factor the numerator is mainly so that in case there's any zeros and poles that are the same, that they would be canceled out. And it may not be obvious that that's the case until we factor things. Okay, so I've come over here to do that on paper. So we have the first term here, I'm just going to multiply out the numerator. So the 18 times 2s plus 3 becomes 36s plus 54. 3 times 18 is 54. And then we have to subtract this part. And so I'm going to just keep the one denominator here, the 4s squared plus 14s plus 1, and put the s up into the numerator there. So we have minus 4 over s times the 4s squared plus 1. That's one way of doing it. And now, basically, I'm going to multiply both the top and the bottom to clear that fraction by s. And so that puts an s in the denominator, which I could have done to begin with perhaps, but I'm just doing it this way. And then we need to multiply this whole thing by the s. So this 36s becomes 36s squared, plus 54 becomes plus 54s. And then we multiply this out so that we can simplify the polynomial. So we have minus 16s squared there, since the s is gone, and then minus 4. And having done that, then we can simplify that a little bit because we've got 36s squared minus 16s squared is just 20s squared. Then we have the 54s minus 4, and that's all good there. And then we still have the same denominator. Now, in preparation, because we're going to have to factor both of these quadratic terms, it helps to normalize both of those terms so that the coefficient of the highest power of s is 1, which in this case is s squared. So what that means is I'm going to factor a 20 out of the numerator to make that true, and then I'm going to also factor a 4 out of the denominator. And since I've got a 20 over a 4, I'm just going to write that for brevity as 5 here. And then this becomes s squared, and we divide 54 by 20. That gives us 2.7. And then minus 4 over 20 is minus a fifth, or minus 0.2. Then in the denominator, remember we have the s, and we factored a 4 out of there to make this 5. So that's going to be s squared plus 14/4 s, which is 7/2, or 3.5. And then the 1 divided by 4, of course, is just 0.25. So now we've rationalized that in the sense of making these coefficients 1. Makes it a little bit easier to do the factoring down here. Okay, so now we need to find the roots of both the numerator and the denominator. So we'll use the standard quadratic formula. If ax squared plus bx plus c equals 0, then the formula that I've always advocated you use is x is negative b over 2a plus or minus the square root of that same term squared minus c over a. That's a very convenient form to use here. So plugging that in for the numerator, our b is the 2.7, so we have negative 2.7 over 2. The a is already 1, so we don't need to worry about the a's. And then we have that plus or minus the same thing squared, and then minus c over a. So c in this case is negative, so that'll actually be plus 0.2, and the a, of course, again is 1. So now, evaluating that with a calculator, we get plus 0.07215 and minus 2.772. Both of those are always in units of inverse seconds because this, again, is a frequency. It's per unit time. Now, you might notice something unusual here, which is this positive value. And you might wonder, is that a mistake or is that something wrong? Well, it's not a mistake, and it's actually not a problem when we're doing the numerator. If we did get a positive value for the denominator, in other words, this is going to be a 0, basically. If we got a pole like that, that would be a big problem. That would mean our circuit is unstable and the response is going to blow up in time. But in the numerator, it's okay. It's not a problem in the numerator because it's a 0 rather than a pole. So even though that's very unusual, well, somewhat unusual, and you may not have seen it before, but it's okay. All right, so in the denominator, we do a similar thing. We have the negative b over 2a is negative 3.5 over 2, plus minus that same thing squared, minus now the c over a. And because this one's positive, it's the usual minus 0.25. And once again, we just do the math there. And that's minus 0.07295, and then minus 3.427, again, inverse seconds. Notice that these two values are quite similar, but not the same. And again, I caution against excessive rounding. That can cause a lot of problems. And people are sometimes tempted to round to 1 or 2 digits because it's a small number. Don't do that, or you'll have problems eventually in getting your answer accepted. So make sure that you carry at least 3 or 4 digits. I'm just doing 4 here to be on the safe side. Okay, so now we can use these roots to factor this. So we have 5, and to factor the numerator, I'm going to write it as s minus this value. So we have that minus this value, and then s plus this value. You have to change both signs so that these, in fact, are going to be zeros and make this thing 0 when we put in either of these two values. Otherwise, it wouldn't work, as you can see. And then in the denominator, we have the s that remains, and then the quadratic then becomes factored as in with these values. So s again plus this value, and s plus this value because this one is negative. And again, the signs are very important there, so always make sure that you're doing the algebra correctly. Okay, so that is our factored expression. So that's now suitable to enter into Circuit Tutor. So we'll type 5 times s minus 0.07215. And of course, always be careful with your 5s and your s's, because if you're not real distinct on those, you could get them mixed up and make a mistake. Okay, and then we have s plus 2.772. And then we're going to divide that, and now we need to use a square bracket to enclose the multiple terms. So that will first be s, and then open parentheses, s plus 0.07295. Close that parentheses, open another, s plus 3.427. Lots of numbers. And finally, close that with the square bracket. Okay, so I'll just proofread that a little bit here because I don't want to make a mistake. And looks like that's good, so we'll check that. And indeed, that is correct. Okay, so now, since we have the complete current, complete sock current after using superposition, we need to do a partial fraction expansion of this. Okay, so we'll select the partial fraction expansion type here. And because we have 3 poles in the denominator, 1 at the origin and then 2 others on the negative real axis, that means we're going to need 3 separate terms for our partial fraction expansion. So 1, 2, 3. And they will all have units of amps here. So we'll set the unit to be amperes as opposed to volts or watts. And then we need to work this out. So I've done that again on paper. So we have this expression, and now I set that equal to a over s plus b over this term, s plus 0.07, etc., plus c over this term, which is the s plus 3.427. And then we once again use the heave-aside method, or the method of residues, to multiply by s, canceling out this and putting an s in the numerator here and here. and then we set s equal to 0, which gets rid of those terms, gives us a on the left-hand side, and over here then we just set s equal to 0. Now, it's actually a little bit better here to come up to the unfactored form because that makes it easier to do the math. So here I'm going to just use the unfactored form and set s equal to 0 up here because that's equivalent to this. And so that just means these terms go away and I get 5 times minus 0.0. Oh, I'm sorry, I wrote that incorrectly here. It should be minus 0.2, but I actually computed it with the correct value that should be, but that's a typo there. Okay, so, and then divided by, again, the s is gone, and then these terms vanish, setting s equal to 0, we have 0.25, and so that works out with the corrected value of minus 4. Then for the b term, we multiply it through by this denominator, and now I pretty much need to use the factored form. To compute that then, I have the 5, and then I set s equal to the negative 0.07295. So that becomes that, and then minus this constant that was already there, and then again substitute s as the same value here, plus that value, okay? In denominator, again, we put in the s, and then this term is the one that canceled, and so we just have this term, which is, again, minus the s value plus the 3.427. And so we have some arithmetic to do there, and that works out to 8.003 to 4 digits. 3 would probably be adequate for the answer, but I just left all 4. Okay, then for C, we do a similar thing, multiply by the s plus 3.427. That cancels out this term, and then we set s equal to the negative of that, which wipes out these two terms since they have now a factor of 0 and gets rid of this. And so then we have the 5 times that negative 3.427 minus this constant, and then the next one, again, put in the s, that same value, plus this constant, and then we put in the s value down here, and then the s value in this term, which is the one that survives, plus that constant, and this one is gone because it canceled. And then we just do the arithmetic there, and that constant works out to 0.9968. So now we can go ahead and enter those values. So the a is negative 4, so I'll put a minus sign there and a 4, and then that's going to be the a over s term. And then the b term, let's see, that was the 8, and I'll just put 8, that's good enough. And then s plus 0.07295. And then the c term, yeah, I'm just going to round that to be 1, save some typing here. That's close enough for the accuracy criterion. And then that divides by s plus 3.427. Okay, so that should be good. So now I'll check that. And that is correct within the typical about 1% error. And so now we've done all the equations of this type, so we just put that proceed button, and it tells us now we have to do the inverse Laplace transformation. Okay, so it's put us in that mode. Now we select the appropriate selection there to give us the terms, and we have I naught of t. And it also reminded us that there is an extra set of terms if we need them there, but in this case we don't. So I naught of t equals, and now I'm going to have 3 terms, all of which are going to be the same. Well, this one's a constant term actually, so I'll use a bracket, but everything has to multiply u of t, and so I'm going to use brackets to do that. I don't think it allows you to put u of t on every single term. So we'll put a constant there, and then we'll put 2 exponential terms because we hopefully recognize that these are in the form of a constant or s plus a, where the a would be a rate constant here for both of these. So they both have the exponential terms. Then we put a closing bracket, and we put our u of t term on the outside, multiplying everything. And then we'll set the units of that to be amperes because, again, it's a current. And now our sought value, our constant value would be negative 4, because it's 4 times u of t in the time domain. And then here we'd have the 8. And remember, it has to always be a decaying exponential, so that's going to be negative. And then that's the, well, now we need the time constant, which is the reciprocal of this rate constant. So I computed that over here. And on the calculator, that's 13.71, or I'll just call it 13.7. 3 digits should be enough there. And then over here, we have the coefficient in this case was, well, we just used 1. And then that has to be negative. And then the reciprocal of the 3.427 inverse seconds is 0.292, let's call it. Again, always use at least 3 digits to be sure you're accurate enough. And we'll check that. And that is correct. So that's been printed here. And now we just have to say no more equations. And it'll do the usual PDF transcript of our work, which we can use to review or study later on. And you can access that from the review work button on the level menu for this game. Okay, and it'll also offer to give us a detailed explanation. And that would show us all the steps that we took here. Since that's rather lengthy, I'm going to skip that in this instance, but if you want to see all of that work again, you can certainly do that and look at that to review. Okay, and this is the review work button, so that concludes this exercise.